السلام عليكم ورحمة الله وبركاته طلابي وطالباتي الأعزاء في مساق Discrete Mathematics. ستكون هذه المحاضرة كما وعدتكم في المحاضرة الماضية مخصصة لمجموعة من الأمثلة حول الفانكشنز وكذلك أنواعها المتعددة Surjective, Injective والإنفرس. الأمثلة متعددة وكثيرة لكنها مهمة بالتأكيد. هذا الشرح الذي اخترته لكم أيضا ضمن سلسلة المواد الإثرائية التي لن تكون بالضرورة ضمن أسئلة الامتحان المباشرة لا في الكويزات ولا في الامتحان النهائي، لكنها بالتأكيد ستعزز فهمكم للفانكشنز وأنواعها، ستعمق الفهم وكذلك ستمنحكم فرصة لأن تستمعوا إلى شرح Discrete Mathematics من نيتيف سبيكر. بالتأكيد المحاضرة هذه شيقة، الأمثلة جدا واقعية وهي احترافية بشكل حقيقي. أتمنى لكم متابعة شيقة ودعونا نذهب لنشاهد هذه المحاضرة. So, let's go!
In this video, we're going to do some questions about functions, so let's dive right into it. First question asks, are the following functions injective, and what is the range? So remember, to prove that a function is injective, we suppose that f of x is equal to f of y, and we have to prove that x is equal to y. Our first function is from the reals to the reals, and f of x is equal to e to the x. So I have a feeling the exponential is injective, so let's prove it. So first we assume that f of x is equal to f of y. So that's the same thing as saying that e to the x is equal to e to the y. Now we can take the natural log of both sides, and we know that the natural log and the exponential cancel, so we're left with x is equal to y. So yes, the function is injective. So what's the range of the function? Well, we know that e to the x grows infinitely large as x gets larger, so it's going to go to positive infinity. And what's the smallest value that you can get from e to the x? Well, the smaller x you put in, the closer and closer it gets to 0, but it never quite touches 0. So our range is going to be from 0 to positive infinity, uninclusive. Okay, so question B, g from the integers to the integers, where g of x is equal to x cubed minus x. I see this x cubed here, I see a minus x, and I also notice that this could be factored into x minus 1, x plus 1, so I'm feeling like maybe these aren't going to be injective. Maybe we can find two values that are equal to each other. In fact, when I see here, when I factor this, it's kind of telling me to look at the values of 0, 1, and negative 1. So we just have to show that two of these are equal, and then we'll know it's not injective. So let's take a look here. Let's take a look at g of 0, and let's take a look at g of 1. So g of 0 is going to be 0 cubed minus 0, and that's equal to 0. And g of 1 is going to be 1 cubed minus 1, which is equal to 0. So we know that g of 0 and g of 1 are equal to each other. Therefore, we have two elements in the domain mapping to the same element in the codomain. Therefore, it is not injective. Okay, and you can also check here g of negative 1, which would end up being negative 1 minus negative 1, which also equals 0. So we can see that there's actually three elements in the domain that map to the same element in the codomain. So what's the range of this? Well, we're in integers, so we can't use an interval. Therefore, our best bet is to use set notation. So our range is going to be the set of n cubed minus n, such that n is an integer. And this will produce all of the outputs. I know it's kind of cheating, because you see, wait, that's the function right there, but this is the range. This is the best description of the range you can give. Okay, so that's the first question. The second question, I want to give an example of a function f from a to b and I want to give two subsets of A, A1 and A2, where f of A1 intersection A2 is not equal to f of A1 intersection f of A2. So what I mean here is if I take the intersection of the two subsets, it gives a different set of values than if I take the function in each of the subsets individually and then take their corresponding values and take the intersection. So a nice way we can do this is we can say, okay, let's let A equal 2 elements, and we're just going to put one element in each subset. So let's say A equals 1 and 2. We're going to say that A1 is equal to the set containing 1, and A2 is equal to the set containing 2. So the nice thing about this is that f of the intersection of A1 and A2 is going to be the empty set. So this is f of the empty set. And when we put the empty set into a function, what do we get out? Well, we get the empty set back. So now we also need to figure out what f of A1 and f of A2 are. So we need our codomain B, and what would be nice is if we could get 1 and 2 to map to the same thing. So we're going to say that B is just 0. Okay, and we're going to define that f of A1 is, so I might define this a little bit more clearly along the right here. So we're going to say that f of 1 is equal to 3, and f of 2 is equal to 3. So f of 1 is equal to 3, f of 2 is equal to 3. So when I put f of A1 in, we're going to get the set containing 3 back. And then when I put f of A2 in, we're also going to get the set of 3 back. So this means that f of A1 intersection f of A2 is going to be the same thing as the set containing 3 intersection the set containing 3, which is just the set containing 3. So we've defined a function, a domain, a codomain, and two subsets such that the f of the intersection of A1 and A2 is not equal to f of A1 intersection f of A2. So that was more of a tricky theoretical question, and the best thing you can do is do very, very simple sets, very, very simple functions. Don't be thinking of a formula like, can I think of an x cubed? Does it work with x squared? You don't need to worry about that. Work with a couple elements and make them do what you want them to do if you can, and do it as simply as possible, because if I used more than 2 elements in the domain and 1 element in the codomain, things might have gotten very tricky. In this video, we're going to do 2 questions related to surjective functions and counting. So for the first question, we want to show that f from R to R, where f of x is equal to x cubed, is surjective. So what this means is we're going to set y equals to x cubed, and we want to show that each x has a unique y, or sorry, all y's are going to be able to be produced from values of x. So what we can do is we can take the cubed root of both sides. So the cubed root of y is equal to x. And here's this question, is the cubed root of y in the real numbers? And yes, it is. So we need to make sure that this is going to be in our reals. And what this says is that we can put in as many values of y that we want, and we can always get an x back. So this function is surjective. And that was a very, very quick proof. The fun thing about this is that it's also bijective, because we can take f of y equals f of x, and we can prove that x is equal to y. So we're good there as well. So this is a bijective function, which means it also has an inverse. And this is going to be its inverse, where the cubed root of y, or the cubed root of f of x, is equal to x. So very basic question, but This is one you normally see on midterms, and they're normally not much harder than this, so that should be good. The next question is a little bit more abstract, and this is a counting question. So if I have the size of A is equal to 4, and I have the size of B is equal to 6, and I ask you, how many functions from A to B are there? So let's think about our function requirements again. So we have 4 elements here, 1, 2, 3, and 4, and we have 6 on the right side here in our codomain. And what's the requirement for a function? Well, it says that everything in our domain must map to something in our codomain. So let's think about this. Our first element has 6 options it can map to. Our second element also has 6 options it can map to. Our third one has 6 options it can map to, and our fourth one has 6 options it can map to. Therefore, our result is going to be 6 to the 4. So we can also think of this as the cardinality of B raised to the cardinality of A. And this is a general result. So what this says is that we have the cardinality of B number of options for each element in A, and we have the cardinality of A number of elements we have to do this for. So that's how you solve the number of functions. So here's the question, how many are injective? Well, this is pretty similar to what we just did. Well, all 4 of our things have to map to something. So what we do here is we take our 4 elements and we have to map to 4 of these in the codomain. And there's 6 total. So it's 6 choose 4 that we have to map to. But we also have 4 factorial ways that we can arrange our mappings. So first we order the 4, and then we choose 4 that these map to. So our end result is going to be 4 factorial times 6 choose 4. And this is the same thing as 6 factorial over 2 factorial. So if I do this more clearly, if I expand the 6 choose 4, we're going to get 6 factorial over 2 factorial, 4 factorial. Then we multiply it by 4 factorial. The 4 factorials cancel, and we're left with 6 factorial over 2 factorial. Okay, so how many of these are surjective? What does surjective mean? That means that the codomain is equal to the range. Well, we can't do that because we can only map to 4 things. Therefore, our codomain is never going to equal the range, so we have a total of 0. So in this video, we're going to do some practice problems with inverse functions. So the first question is a proof. If f from a to v and g from b to c are invertible, then g dot f from a to c is invertible, and the inverse of g dot f is going to be f inverse dot g inverse. So let's prove the first statement. If f and g are invertible, then g dot f is invertible. So f and g are invertible, so this means that f is bijective and g is bijective. So because f is bijective and g is bijective, this is concluding that g dot f is going to be bijective. Therefore, of course, g dot f is invertible, since that's the only criteria. As long as it's bijective, then it is going to be invertible. Okay, so that's part 1. Part 2, we need to show that the inverse of g dot f is equal to f inverse dot g inverse. So what we can do is we know that if we take g dot f and g dot f inverse, we're going to get the identity function back. So what we'll do is we're going to take g dot f and we're going to test f inverse dot g inverse in its place and see if we get the identity function back. So we can do some, what I should do is I should put this dot here because we are composing 2 functions here. So first we'll use the associativity law, and we're going to group our f and f inverse together. And with this, we're going to produce the identity function. And this should be an inverse. And of course, the identity function maps everything to itself. So we can get rid of it there. So in the end, we get g dot g inverse, which again gives us back the identity function. Therefore, because inverses are unique, we know that g dot f inverse works as f inverse dot g inverse. Therefore, the two are equivalent. What you have to do on your own is you have to prove that this works on the other side as well, since inverses go in both directions. But you can see pretty clearly that if we flip the side, then the g inverse and g are going to group together first, and then f inverse f will group together, and you'll get your final result back. So that's the first question. The second question says, let f be a function from reals to reals, where f of x is equal to x squared, and I want to find this f inverse y for each set y. The problem here is that, of course, f of x equals x squared is not bijective. So calling this the inverse doesn't make any sense. So in this case, when we deal with this notation f to the negative 1 of y, where it isn't bijective and there's no inverse, what I'm really asking for is the pre-image. So the pre-image is going to be a set or interval. It is not going to be an element on its own. It's going to be a set or interval. So I'm asking for the pre-image. I'm asking for everything that maps to the set y using the function f of x is equal to x squared. So the first example, if we have y is equal to the set 0, 1, I'm saying, okay, what values give x squared equals 0 and x squared is equal to 1? So f inverse of y, well, what squared gives you 0? Well, 0 squared gives you 0. What about what squared gives you 1? Well, negative 1 squared gets you 1, and 1 squared gives you 1. So our pre-image of y is going to be negative 1, 0, and 1. Okay, so what about the interval? So in this case, we want x squared to be between 0 and 4. Okay, so, well, this is just like taking the square root of both sides. So when we take the square root is going to be between negative 2 and 2. Because remember, the square root of 4 can be negative 2 or 2, and the square root of 0 is just going to be 0. So x can be in this whole interval here. So our pre-image of y is going to be negative 2 to 2 inclusive. Okay, what about this? From 4 to 9. So we want x squared to be greater than 4, but less than 9. So what happens when we take the square root? Well, we get 2 is less than x, which is less than 3, and, I should say or, negative 3 is going to be less than x, which is going to be less than negative 2. Because remember, when we squared the negative numbers, they also become positive. So we have these two intervals here. So if we take the pre-image of y, then we're going to get from negative 3 to negative 2, union 2 to 3. So this is kind of like asking for the domain when you're given the range. It's pretty much the same thing. So that was some questions about inverse functions and preimages. In this video, we're going to tackle some more questions with inverses. So for the first one, we want to show that f of x is equal to mx plus b from r to r is invertible, and we want to find the inverse. So how do we show it's invertible? Well, we need to show that it is a bijective function. So we need to show that it's injective, and we need to show that it's surjective. So, injective. If f of x is equal to f of y, we need to show that x is equal to y. Okay, so let's substitute f of x and f of y in. So we're going to have mx plus b is equal to my plus b. We can subtract b from both sides. So we're going to get mx is equal to my. Then we can divide both sides by m, and we're going to get x is equal to y. So we're good. Next one is surjective. So what we'll do is we're going to set y is equal to mx plus b, and we're going to solve for x. Okay, so we're going to get y minus b is equal to mx, so y minus b over m is equal to x. So if we pick any value for y, we're going to get a corresponding x back. So it is surjective. So every single y we can think of, we can put in and we'll get a unique x back. So we're good. Okay, and what is the inverse? Well, we solve for the inverse. So y minus b over m is equal to x. Okay, so that is the inverse, and we've shown that it is invertible. So this one, we want to show that x plus 1 over x plus 2 is bijective for f from the reals minus negative 2 to the reals minus 1. So this will work. We won't run into any domain or range restrictions here. So first step, we want to show that it's injective. So again, we start with f of x is equal to f of y, and we want to show that x is equal to y. So we're going to have x plus 1 over x plus 2 is equal to y plus 1 over y plus 2. We can cross multiply here. So we're going to get x plus 1 times y plus 2 is equal to y plus 1 times x plus 2. We're going to multiply these out. So we're going to get xy plus y plus 2x plus 2 is equal to xy plus x plus 2y plus 2. Okay, we can subtract xy from both sides. We can subtract 2 from both sides. So we're going to be left with y plus 2x is equal to x plus 2y. We're going to bring all the y's to the right, all the x's to the left, and we're going to be left with x is equal to y. So it's injective. Okay, now we have to show that it's surjective. So we're going to have y is equal to x plus 1 over x plus 2. We know that x cannot be negative 2 here. We're fine because we're looking in the domain without negative 2. Okay, let's multiply. So this is y x plus 2y is equal to x plus 1. Again, I just multiplied and distributed immediately. We're going to bring all the x's to the left. So we're going to have yx minus x is equal to 1 minus 2y. We're going to factor out the x here. So we're going to have x times y minus 1 is equal to 1 minus 2y. And we'll divide both sides by y minus 1. So x is equal to 1 minus 2y over y minus 1. We see y here cannot be equal to 1. That's fine, because we're looking in the codomain where it's all the real numbers except for 1. So don't worry, I double checked this time. This video, it's good. So we've shown that, yes, this is going to be in the reals, assuming that, of course, y is not equal to 1. So it's surjective. Okay, so now we've proven that it's bijective because it is both surjective and injective, and therefore the question is done.
في ختام هذه الأمثلة المتعددة أتمنى أن تكون قد أثرت معرفتكم وخبرتكم وإدراككم لأنواع الفانكشنز وتطبيقاتها المتعددة وتطبيقات أنواعها أيضا المتعددة، وذلك لأهميتها لطلبة هندسة البرمجيات. الفانكشنز هي محور البرمجة، الفانكشنز هي محور الداتا مايننج، الفانكشنز جدا مهمة. إلى أن ألتقيكم في المحاضرة القادمة، أتمنى أن تكونوا بخير، والسلام عليكم ورحمة الله وبركاته.